Next up, what we're going to do is we're going to talk about what are called similar matrices. Let's say that we have two matrices A and B. So let's let A and B be two n by n matrices. And we say that A and B are similar, or sometimes we say that A is similar to B and B is similar to A. But anyways, we say A and B are similar if there exists an invertible matrix. So if there exists an invertible matrix P such that A is equal to P inverse times B times P. Okay, so if there's such a matrix P, we say that A and B are similar. Some books have this the other way. This is equivalent to saying that A is equal to some invertible matrix, say Q times B times Q inverse. So some people like to put the inverse on the right side. Some people put it on the left. I put it on the left because that's what the book does. But really, they're similar. If Q is equal to P inverse, then Q inverse is equal to P, and everything is the same anyway. So this is trivially equivalent to, these are two trivially equivalent statements. So we say that A and B are similar if such a P exists, so that you can write A as P inverse times B times P. Just for example, just to compute a actual concrete example here, let's look at the matrix. So let's look at the matrix A, which is 5, 2, negative 5, 3. It turns out A is similar to B, where B is the matrix 1, 2, 3, 1. And you can check this. So you can check that the matrix P is given by 1, 0, 2, 1. So that P inverse is given by, remember, for finding inverses of 2×2 matrices, you switch A and D. So those ones switch places, so they still look like ones. And then the off-diagonal values you make negative. So negative 0 is still 0, negative 2 is negative 2. So it turns out that if you check P inverse times B times P, you get A. So A and B have, they're similar matrices. So A is similar to B, and likewise B is similar to A. It turns out, there's lots of properties here, but it turns out that similar matrices have a lot in common. So it turns out that similar matrices have the same, no surprise, but they have the same determinant. They have the same trace. They have the same rank, and therefore the same nullity. And there's lots in common with these similar matrices. Let me just show you how to prove this first property about the determinant. This really just goes back to something that we know already about the determinant, and that's that the determinant of a product is the product of the determinants. So the determinant of A is the determinant of P inverse BP, and we know that that's the determinant of P inverse times the determinant of B times the determinant of P. So that's a property that we've talked about before. And it turns out that the determinant of P inverse is 1 over the determinant of P. And so those end up canceling, and what you end up with is really just the determinant of B. So the determinant of A and the determinant of B have to be equal if A and B are similar matrices. The trace is proved similarly. The rank is a little bit more involved. There's a lot of subtlety here. It's actually really hard if I give you two matrices, it's really hard to determine whether or not they're similar. Certainly you can compute their determinants and their traces. And if the determinants and traces are unequal, that tells you that they must not be similar. But it's really hard, and actually even worse than that, even if you know that two matrices are similar, finding that matrix P is also really hard. So again, there's a little bit of subtlety here, but this is what similar matrices are. One more property that I just want to share here. If I were to look at powers of similar matrices, so if A is equal to P inverse times B times P, and if I were to look at, say, A squared, what would happen? That would be P inverse times B times P times itself, P inverse times B times P. And notice that because of the associativity of matrix multiplication, I can undo the order here. Oops, I didn't mean to bring all that. But I can undo the order of the products. I can look at P times P inverse. That's really just going to be the identity. So that's gone. And what that means is that you're left with P inverse times B times B times P. And so that's nothing more than, let me put this all back together, but that's nothing more than P inverse times B squared times P. And so that's A squared. And in fact, you can do that argument as many times as you want. And it turns out that A to the n is going to be Pn times B times P n times, right? So P inverse B P all the way down to P inverse B P, P inverse B P. Let's say that we've done this n times. Okay. So n times. And think about what's going to happen. We know by associativity we can basically get rid of all of the parentheses. We know that if I take P times P inverse, those will cancel. So all the inner P and P inverses, I'm assuming that there's some missing P and P inverses here where the dots are. All of those cancel. And all that we're going to end up with then is the P inverse at the start. So we end up with the P inverse on the left. We have B n times, so that's B to the n. And then we have this P over here on the right. So that's a nice property that similar matrices share. Okay, that's similar matrices in a nutshell.